Ian Olmsted is the product manager for CEM's Process Control Division. With over 10 years of experience developing analytical instrumentation, he is passionate about creating new products to give his customers a competitive edge. In his spare time, Ian enjoys traveling and restoring classic cars. So thank you for joining us today, Ian. I'm going to turn the presentation over to you.
Thank you, Rita, for that introduction, and I want to thank everybody taking the time to join me for this webinar today. As Rita mentioned, we'll be discussing ignition and drying methods such as USP 281 and USP 731 and how to safely perform those without sacrificing performance. Just to give you a little more background on myself, who you're listening to today, my name is Dr. Ian Olmsted. I got my PhD in analytical chemistry. I did that at Vanderbilt University, and currently I am the product manager for CEM Corporation's Process Control Division. Here's an outline of what I'd like to discuss today. First, we'll cover loss on ignition. There are some questions that you can ask yourself to help you improve your process. First, why do I need to do it? What is loss on ignition? Why is it important? Secondly, we want to cover what the risks are of loss on ignition and how you can do it more safely. And finally, we'll cover how to reduce test times. After we cover loss on ignition, we'll discuss loss on drying. We'll discuss why you need to do it, what the risks are that are associated with that test. We'll discuss loss on drying and how that differs from other methods such as Carl Fisher. And we'll discuss rapid alternatives and what you can look for to speed up your loss on drying testing without sacrificing safety or performance. So let's get started with loss on ignition. Loss on ignition. Why do I need it? Loss on ignition determines the ratio of organic to inorganic material. In the pharmaceutical industry, that's important as an indicator of purity and quality, and it ensures consistency in drug dosage. There are a lot of different ways to calculate that ratio of organic to inorganic material, but the most common ways that you'll likely run into are loss on ignition, or LOI for short, and residue on ignition, ROI. For our purposes today, we will focus on sulfated ash, which is a bit of a specialized way to perform loss on ignition. Here's a little quick background on sulfated ash. There are many standard methods for performing sulfated ash. It's very common in the pharmaceutical industry, but also in other industries as well. For pharmaceutical, the most common method is USP 281, but if you're in the petroleum industry or looking at oil, there are ASTM, IP, and other methods as well. So it's a fairly broad method with good applicability in the pharmaceutical industry. So first, let's take a look at what the traditional steps are to perform a sulfated ash analysis. So similar to any ash analysis, you would start by pre-firing your crucibles in a furnace. This is to drive off any residual moisture. Then you would place that fired crucible into a desiccator to cool and dry. Once that crucible is cool and dry, you'll weigh it to get that tare weight of the crucible. Once you have the dry crucible tared, you will weigh out your sample, and then you'll add acid. Typically that's going to be sulfuric acid, and then the next step is to pre-char that sample over typically a Bunsen burner, or it could be over a hot plate, or it needs to be heated in some way to pre-char that sample. Once the sample is pre-charred, then it is placed in a muffle furnace and ashed at the specified temperature. That's typically going to be around 600 degrees. That ashing time could take anywhere from 1 to 8 hours. After the ash is complete, users will need to check the weight of the sample, then they'll add additional acid and re-ash and continue that process until constant weight is reached. So once you have ashed your samples and they're no longer losing weight throughout the ashing process, it's time to remove those samples to cool in a desiccator. The crucibles will stay in that desiccator for about 1 hour, and at that point, once your crucible is cool and dry, then you can measure and record the final weight. Altogether, these manual steps can be fairly time-consuming and can take up to an entire shift to perform. So now I'd like to cover some of the risks associated with the traditional sulfated ash method. The first one, and most obvious here, is safety. You're dealing with open flames, very high temperatures. You're dealing with acid and potentially dangerous reagents as well. So during that pre-ash step, extreme care must be taken not to overheat the samples. If you heat too fast and the acid boils over, you could create a fire, you could burn the sample. So it's very important that extreme care is taken during this step. More on safety. Crucibles retain a lot of heat, especially ceramic crucibles, and so even after that crucible has been pre-charred and set down, once it stops glowing red, it still remains hot for a long time. So the more manual steps involved in the process equals more opportunities for users to burn themselves. So that's something to be very careful about. Beyond personal safety, there are also risks to quality of results, risks to the sample itself. So with a lot of steps, we have a lot of chances for human error, particularly in the pre-ash step, but also inside the oven. If the samples are heated too quickly, if you have poor temperature control in your muffle furnace, then that will result in loss of sample and results will be falsely low. If you take a look at some of these pictures down below, here we have some examples. On the left, you can see a sample that foamed up as it was placed into the oven, and that crucible is not retaining the sample entirely. On the right, you can see some very obvious splattering and loss of sample there as well. In the middle, maybe not quite so obvious, but around the rim you can see a little bit of splattering, showing that some of your sample was lost and your results are going to be inaccurate. So a couple ways to avoid this is to slowly ramp up to temperature, make sure you have good temperature control and you're not heating that sample too quickly, and also make sure that you have the right crucible size. It's important to have a crucible that's large enough to contain that sample because some samples do foam up, and that's the nature of how they react to being placed in the furnace. So understanding your samples, understanding your setup is very important to safe and successful sulfated ashing. One more risk is the environmental risk of not only sulfated ash, but just ash in general. So in general ashing, soot is generated from burning that sample. So it's important to make sure that that soot is being handled properly, that those fumes are being pulled away and out of the lab so that laboratory personnel are not exposed to that soot. Same goes for acid vapors in the case of sulfated ash. It's important that those acid vapors that are being generated are properly handled, not only to avoid personnel being exposed, but also laboratory equipment. Acid vapors are extremely corrosive and pose some dangers to lab equipment as well, such as fume hood blowers. So some questions to ask yourself: are the contaminants you're generating in your sulfated ash test coming into contact with staff? And the other question is, are these contaminants contacting and degrading lab equipment? The things to consider when you're designing a setup for sulfated ash. One final risk, and one we may not think about too much, is time. So time equals money, as they say, as the old adage goes. Labor in most parts of the world is quite expensive, so if we can make a test safer, if we can maintain good accuracy, and if we can save some time, we can have our cake, we can eat it too. So time spent waiting on batch release is expensive, so if you have a process where batch release is dependent on ash analysis, then this is one way to remove the bottleneck that I'm about to discuss with you. And if we can eliminate pre-ash and post-ash steps, we can save some time as well. Now that we have covered the traditional way of performing sulfated ash and the risks associated with that test, I'd like to introduce a more automated approach that employs active ventilation and a scrubber system that allows the pre-char step to be performed inside the muffle furnace. The scrubber system captures acid vapors and neutralizing them, shown here on the left of CEM's Phönix Black muffle furnace. Before I get into the details of how the acid neutralizing system works, I'd like to spend a brief moment on the Phönix Black muffle furnace itself. Unlike most other muffle furnaces, the Phönix Black uses microwave energy to heat a silicon carbide element within the furnace, shown on the right-hand picture. You can see it glowing orange. That heating element absorbs all of the microwave energy generated by Phönix Black. It's important to note that the sample is not exposed to microwave in any way. So not only is your sample not being exposed, but same goes for crucibles. What that means is you can use any type of crucible inside the Phönix Black muffle furnace, including platinum. In addition to the unique heating design, the Phönix Black also uses active ventilation, which not only speeds up the ashing process, but also allows it to be operated anywhere in the laboratory. It does not need to be placed inside a fume hood. So we are able to reduce the number of steps required to perform sulfated ash due to a number of features on the Phönix Black. The first one is the complete scrubber system with carbon filter that allows for acid vapor neutralization. We also have active ventilation, which means that once the sample is placed inside the muffle furnace, there's no exposure of acid vapors to personnel or to other lab equipment. Because everything is performed inside the furnace, there are no hot acid samples to handle. There are also no hot outer surfaces, so once the sample goes into the furnace, everything outside is safe to the touch. So now that we have a general background on Phönix Black, what it is and how it works, I'd like to discuss a typical automated sulfated ash method that is possible with the Phönix Black when a scrubber system is used. So instead of the 13 steps that we went through before, we have a streamlined process here. So it starts just as with the traditional method in weighing out the sample in an appropriately pre-dried crucible. Just with the other method, we'll also add acid to the sample, but this is where we have some differences. Instead of pre-charring that sample over a Bunsen burner or on a hot plate, users are able to simply place the sample into a cool furnace, meaning less than 175 degrees, and then they can start a method through the Phönix Black software. That method will slowly ramp to about 5 or 10 degrees above the boiling point of the acid, depending on how that method is written. And then it will hold for 15 to 60 minutes at the specified ash point to completely ash the sample. And again, that's going to be sample dependent, so the methods are editable based on the needs of each sample. Once the method is complete, the user will remove the crucible from the furnace, place in a desiccator as normal, and finally record the weight of the sample. Let's focus a moment on the acid vapor scrubber system. So we have a small vacuum pump that places negative pressure on the furnace insert and pulls all acid vapors that are generated throughout the process through 3 scrubber bottles and a carbon filter. So the air coming through that pump then is completely pH neutral and devoid of any soot particles. But the scrubber system is only half of the equation. The other key feature that allows all steps of this sulfated ash analysis to be performed inside the muffle furnace is the ability to precisely control temperature at every step throughout the process. We do that with a NIST traceable thermocouple and easy to program methods that automate the process. So with this software and with the scrubber system, users can simply place that sample inside the furnace, select the method, and press start. Here's a quick look at what the method editor looks like for Phönix Black. It's very simple and straightforward. It provides complete control of temperature ramps as well as dwell times, scrubber pump activation, and any other parameters that you want to control throughout that sulfated ash test. Here's what a typical method would look like. So we start out by slowly ramping to the boiling point of the acid. That's a controlled ramp set rate of temperature increase over time. Once the unit reaches the boiling point of the acid and all the acid vapors are driven off, then the furnace can rapidly heat to that final ash temperature. Again, that's typically going to be about 600 degrees. And then we'll hold for a specified amount of time, at which point the test will be over and the crucible can be removed, desiccated, and measured. So here's a little bit of data to show how this compares to a conventional muffle furnace method. So I will point out that when you look at the times associated with each of these tests, that this is a fairly conservative comparison because in the Phönix Black column, we are including that pre-ash step as well as the final ashing step, whereas in the conventional muffle furnace, we're only looking at the final ash step. So if you look at times for the conventional method, we're looking at anywhere from 1 to 9 hours, whereas with the Phönix Black, you're looking at anywhere from 10 to 40 minutes. So significant time savings in addition to a safer method. As you can see by the results, they match up very well between the conventional and the Phönix Black method. So still getting good data, saving some time, and improving safety. So to summarize our loss on ignition section, with the right setup, you can perform all sulfated ash steps inside of the muffle furnace and get rid of the manual pre-ash step. Because there's no manual pre-ash step and all soot and vapors are neutralized, with the setup I've shown you here, users are not exposed to any safety risks such as open flame, things like that. With active airflow, ash times are significantly reduced, so we go down from 9 hours to as little as 10 minutes, and final results match very well with the traditional method.